So what we're going to do next is kind of put everything together, which I think is something that's really cool, how we take all the pieces that we learn and then we apply it to one problem. So we're going to use derivatives to graph a function of higher power. So something that's greater than power 2. These quadratics, we can factor, find vertexes and all that stuff. The only other way that you have graph problems like this is using the rational root theorem in algebra 2, where you had like the p's and q's and you did synthetic division and found all the roots and all that stuff. So here we're going to find a little bit more information about it. So the first step that we're going to do is find the derivative. So we don't have to do any limit definition here. We just need to use the power rule since that's what we have now. So this exponent multiplies to the coefficient, becomes 6, take 1 away from the exponent. 2 multiplies to the 3, take away 1 from the exponent. And then you can say power 1, multiply to the 12, and then take the 1 away. So there's our derivative. So my next step is to set that derivative equal to 0 and find some critical points. So what I get from solving this, I'm going to put onto the wave, and we're going to find some information about it. So in this problem, I could factor out a 6, or I can divide it all out and end up getting x squared plus x minus 2 equals 0. We can factor it to x plus 2x minus 1 and find out my 2 points here are negative 2 and 1. So I'm going to put that on a wave. So negative 2, 1, leading coefficient is positive, so we go through each one of those. Now, this is the wave for the derivative. So this tells us a lot more different information than what the wave did for our function. The wave for the function tells you where your y values are positive or negative. For the derivative, it's going to tell us the slope of the derivative, if it's positive or if it's negative. If the slope of our tangent lines are positive, that means that our function is increasing. Okay, so our function is increasing from when our derivative is positive. Same thing over here. Our graph is going to be increasing. Then down here at the bottom, we have that our tangent lines, our slopes are negative. So this is where our function is decreasing. So where f is decreasing, where f is increasing, and increasing over here. Well, what's really cool about doing the wave for the derivative is that if we know that a function is increasing and then it starts decreasing, so think about that, what that looks like. So it's increasing, stops, and then decreases. That creates kind of an upside down parabola. And upside down parabolas have a maximum point. So that means if the derivative wave goes, from positive to negative, then we have a maximum value. If our function is decreasing, so think about what that looks like, and then it starts increasing, it looks like a U-shaped parabola. So that means we have a minimum value at that point. So then what I need to do is figure out what are my outputs for these very special x values. Now, you have to be very careful with plugging it into the derivative. If we plug in an x value into the derivative, we get the slope of that tangent line at that point. What I really want to know is where is that maximum minimum value? So if I plug in negative 2 into my function for every x, so we're plugging it into this function here, you end up getting an output of 21. If you plug in 1 for every x that you see in the original function, you end up getting negative 6. So our function ends up having a point at negative 2, 21 and at 1, negative 6. Well, from the wave of our derivative, we found out that at negative 2, we get a maximum value. So that means this point here is going to be my maximum point. At this point here, we talked about how it went from decreasing to increasing, so we have a minimum. So this ends up being a maximum point and a minimum point here. So part D asks us to find the interval where the function is increasing. So we need to look at the wave of our derivative. If the slopes are positive, my graphing is going to be increasing. So it's going to be increasing from all the way to the left, which is negative infinity to negative 2. Now, what happens at negative 2? It depends on who you're talking to. There are some textbooks and teachers that say at a maximum or minimum point, the graph is both increasing and decreasing. There are some teachers that say, well, it's doing neither. And some books even say, like, no, at a point, it is not increasing, nor is it decreasing. So it all depends who you ask. In this class, what we're just going to do is we're just going to put parentheses on that. So at -2, we're just going to say that it's not increasing or decreasing. If you put a square bracket here, you're saying that it does both, which is fine. Either one is an acceptable answer on the AP exam. But for now, we're just going to do parentheses. So since my graph decreases and then increases again, that means I have another interval starting at +1 and going all the way to the right to infinity. So again, I could change these to square brackets. Doesn't change anything. You get full credit on an AP exam as well. Where is it decreasing? Well, it's decreasing from -2 to 1, and we're writing this as interval notation. We're not doing inequalities. Do it as interval notation using parentheses or square brackets. And remember that these aren't points. These are intervals in which my graph is increasing or decreasing. So what I want to do here is I want to identify the relative maximum value, which is telling us what is the y value at that maximum value. Well, we figured that out here. So again, dealing with our wave here, we found out that at -2 we have a max. So our y value at that maximum point is 21. Identify the relative minimum value. Again, it's asking for the y value of our minimum. So in that case, it's going to be -6. So what I'm going to do here is I'm going to graph all this information on one graph. I'm going to plot the critical points, my maximum minimums. I'm going to do a y-intercept. Hey, I haven't talked about that yet. Y-intercepts is where the original function, where x is 0. Well, if you plug in 0 into our original function, you get left with 1. So our y-intercept is 0, 1. So let's first draw a grid. So since we're dealing with, a maximum value of 21, I try to think of a scale that would best work out for this. And for myself, I went by 3. So you can go by 1s if you want to go to, by 2s, whatever range you want or scale you want to do it. Just the only thing is that if you're changing the scale for your y, make sure that you scale your x-axis the exact same way and vice versa. So our maximum point is going to be at -2, 21. So I'm going to have a point somewhere here. I'm going to a y-intercept at 0, 1, which is going to be somewhere here. And I have a minimum point at 1, -6. So somewhere maybe here. So then you have to make sure that you're thinking about this correctly. So from -infinity to -2, our graph is increasing. So we're going to go from down here and go this way. Then we're going to come back down and reach that y-intercept and this minimum value and then come back up. So let's see what that looks like when we connect the dots. All right, so what we got here, and you can do a little bit more work if you wanted to. If you wanted to figure out where those zeros are for that original function, you can do that, but it's all just a sketch. As long as your graph is increasing from -infinity to -2, decreasing between -2 and 1, and then increasing from 2 to infinity. It is very important that your graph does not go past those maximum minimum points. So like, for example, I have seen students in the past that do this. Like they draw their maximum point, they draw their minimum point, and they draw their graph, and then it goes past those maximum minimum points. So be very careful with your graphs. Make sure that, when you're curving it, it goes to that maximum and doesn't go past it. And the same thing goes for the minimums. Just make sure that your graph doesn't pass those points. So that's how we make the most accurate graph using derivatives. With the rational root theorem, you found your zeros and you plotted points like that, but you didn't really know how high or low your graph went. So this using derivatives helps us do that. So let's look at another problem. So same thing, we're going to find the derivative of this function. So what we're going to do is use the power rule. So 4 times 2 is 8, subtract 1 from the exponent. 3 times 4 is 12, subtract 1 from the exponent. We find those important x values by setting the derivative equal to 0. So for this one, I could divide both sides by 4, or I can just factor out 4x squared. Now the 4 doesn't really matter. Again, you could have divided it out, but the x squared, when you set that equal to 0, you get 0 double root. You get a multiplicity of 2. And then 2x minus 3, we get 3 halves. So if I were to put that on my wave, I would have 0 and 3/2. My leading coefficient is positive, so I'm going to start off at the top right. 3/2 is only one root, so it's going to go through that, but bounce off 0. That means the slope of my tangent lines from -infinity to 3/2 are all going to be negative. From 3/2 to infinity, it's going to be positive. So what happens if the slope of my tangent lines are negative and then go to positive? What if our graph goes from decreasing to increasing? Well, that means that I have kind of like a regular parabola, which has a minimum point. So at 3/2, I'm going to have a minimum. So our critical points are using these important x values, but trying to figure out what y value we get out from the original function. So if I plug in 0 into my original function, I get out 0. So that means I'll have a point at 0, 0. If I plug in 3/2, and depending on the blend quiz or test or anything, if it's non-calculator, you need to make sure that you're practicing all of that math. But you end up getting -27/8 as the y value. So that means we have a point 3/2 and -27/8. Now is 0, 0 a maximum point, since this point is going to be a minimum? No, because there is no sign change. Our graph is always decreasing. It might do something weird along the way, but our graph is literally always decreasing. So if we're going to give our intervals of increasing, decreasing, increasing is when the derivative is positive. So that means from 3/2 to infinity. I can put a square bracket on 3/2 if I wanted to. And where is it decreasing? Well, it's not decreasing in two different spots. It is always decreasing from -infinity to positive 3/2. If we were to put square brackets, you would kind of understand how we're putting it as one. It goes -infinity to 0, including 0, 0, including to 3/2, which you would write it as one interval. So no matter if we're using parentheses or square brackets, it is still always decreasing here. So make sure to write that all as one interval. So let's identify the maximum value. Well, we don't have a maximum value. We didn't have a situation where we went from an increasing to a decreasing. So there is no relative maximum value. What about the minimum value? Well, yeah, we've figured out that our function is going from decreasing to increasing, so we're going to have a minimum point at here. So that y value is -27/8. Again, leave your answers as exact as possible. Don't bother putting a decimal on that. Oh, we got a new part here. Identify x-intercepts. Well, that's where my function is equal to 0, like my solutions, my zeros. So I'm going to set my original function, 2x to the 4th minus 4x cubed equal to 0. So I can kind of do what I did in part B. I can factor out a GCF of 2x cubed and get left with x minus 2. And if we have x cubed, that means that we're going to have a triple root. You can put TR next to it if you want to, but honestly, that doesn't change anything, because if you have an odd root, it goes through that 0. If it's an even root, it bounces. And then when x minus 2 equals 0, we get 0, 2. So we're going to plot the critical points. Oh, we didn't do a y-intercept, but that's pretty easy. F of 0 is 0. And use the wave to graph the positive and negative slope. So let's draw our grid. So with this grid, what I ended up doing was just using the single kind of tick mark. So each tick mark is 1. So what do we have here? Well, we have a y-intercept at 0, 0. We have a critical point at 0, 0. And then we have a point at 3/2, -27/8. So 3/2 is 1.5. -27/8, it's somewhere between -3 and 4. So I'm just going to say it's here. And then we also have our x-intercept where it crosses the x-axis. So we had one at 0 and one at 2. So what I'm going to do here is I'm going to kind of connect the dots. Now, since our graph was decreasing from -infinity to 0, we kind of have something that looks like this. Now, the idea here, though, is that at this critical point, it kind of flattens out, but it doesn't go back up. It's still decreasing. So we end up going downwards, creating a minimum point, and then coming back up to that 0 and then keeps on increasing. Okay. So you kind of get a graph that looks like that. So your minimum value could curve a little bit better than mine. I try to do that live to kind of talk about when we're decreasing, kind of leveling out, decreasing, and then shoot back up to increasing. So hopefully you kind of see how important everything that we've done all the way from algebra 1, from solving polynomials to using the power rule and derivatives and all that crazy stuff to graph a function on your own instead of plugging in points. So if you have any questions, make sure to bring them to class. See y'all later.